today, presentation is going to be given by Zhaodong Wang. He's a PhD candidate in our group. And according to his bio, he received his BS in civil engineering from Tsinghua University in China. I think it's one of the good universities in China. And I know that Sean, he's also from our group and from Tsinghua University. And he received his degree, a master's degree in applied mathematics from University of Illinois in 2015. That scares me a little bit about this presentation. And that he's now currently working for his PhD under the supervision of Professor Yanfeng Ouyang in our transportation group. So let's just welcome Zhaodong for his presentation, and he's going to be talking about traffic equilibrium problems and planning service facilities under congestion. Zhao?
Okay, good afternoon, everyone, and thank you for coming today. My name is Zhaodong Wang. Today, I'm going to show my recent work on continuous traffic equilibrium problems and planning service facilities under congestion. This is a joint work with Professor Yanfeng Ouyang. And this research containing the following features. First, we designed the facility locations considering the traffic equilibrium under congestion. And second, we develop a closed-form user equilibrium solution for multiple facilities and for arbitrary shaped region. And then we derived some closed-form optimization formula to get the true optimal solution for facility location design. And finally, we conducted numerical experiments to compare our modeling approach with the traditional numerical methods. So to start with, let's take a look at several incidents. First is the Hajj pilgrimage stampede, which killed more than 2,000 people in last year, where people were trying to move around the stone in the center, and this will cause a huge congestion and stampede. And another incident is in Shanghai, China, in the Chinese Square for the New Year celebration, and where people were trying to move to the riverside to see the fireworks. And due to a large amount of the people and the cascading stampede, 36 people were killed and 47 were injured. So this is a very terrible disaster. And also, there are many similar incidents happen all around the world in recent years. So all of those incidents are actually caused by the crowding near the facility, near the service facilities. So those terrible disasters prompt us to analyze the reason behind those terrible incidents. So now I will ask, how could these incidents happen? Actually, the first reason is that the turbulent pedestrian flow. Actually, if the pedestrian density is extremely high, then they will move uncontrolled in multiple directions. And this will put a high pressure on them and leave them in a very dangerous situation. And another reason is that people actually don't aware of the risk of the crowd gathering in such an unsuitable places. And also, the infrastructures for an efficient channelization or guidance of the pedestrian flow is not well designed or even do not exist. So this is not very promising. And a very important reason is that when the planner planning those facilities, planning the location of those facilities, they didn't consider the effect of the congestion. So this is the most important reason that causing those incidents. So also similar problems happen in many different contexts. For example, in some freight industry, for example, the Amazon or DHL, they are actually developing some drones to deliver some packages. And when those drones arrive the bases near the customer neighborhoods, they will suffer a congestion near the bases. And this congestion will cause some extra delay or some traffic diversion. And this will generate more cost for the company. So if we can design the best location, So if we can design the best location of those bases, we can release those congestion and then save some money for the company and reduce the delay of the delivery for customers and even avoid some potential safety issues. So those kind of problems bring us to the research question. The problem I mentioned before can all be categorized into a facility location problem, where the customers are trying to patronize those facilities. For the facility location decisions, we are trying to find the optimal facility number, location, and the corresponding customer allocation. And the target of this optimization is to minimize the total cost, including the facility setup cost, as well as the customer access cost. But there is a balance between them. The number and the location of the facilities will affect the demand and the route choice of the customers. So this will change the congestion pattern in the new traffic equilibrium. And the new traffic equilibrium will in turn alter the delay and the cost, which will affect the optimal number and location of the facilities. So there is a mutual impact between the supply chain planning and the traffic equilibrium. So this whole problem can be treated as an integration of the facility location decision as well as the traffic equilibrium with the customer access cost under the congestion. Now let's take a look at the traffic equilibrium. The traffic equilibrium in a two-dimensional space is actually not an easy problem. Actually, in the traditional, the discrete network model may not be applied to solve this traffic equilibrium problem. Look at this picture. This is an experiment for real pedestrians. We can see that for these real pedestrians, they are moving all directions randomly with continuous direction. And also, if they face some restrictions, the traveling speed gonna be a little bit faster. This means that the flux in all directions may interfere with one another. So the traditional discrete network may not be suitable to solve this continuous traffic equilibrium problem. So that's why this is a difficult problem. And generally, this whole problem can be seen as a bi-level problem, where the lower level is the traffic equilibrium I mentioned before, which is not an easy problem. And this problem is solving the traffic equilibrium given the location of the facilities. And the upper level is how to locate those facilities. So this is two problems, and these two problems are both difficult. For the upper level, only the location decision, there are basically two methods to solve this. One is using a mixed integer program, where people use some integer variables to indicate the location of the location decision. And another method is called the continuum approximation model, where people use the density of the facilities to determine the location of the facilities. For the lower level, the traffic equilibrium, since the discrete network model is not, cannot be suitable to solve this problem, so only a continuous user equilibrium model is applied to solve this, using some partial differential equations and solved by numerical methods such as the finite element method. Now, to combine this location decision and the traffic equilibrium, we previously developed two approaches to solve this problem. One is called the CA model, which is the continuous approximation pretty similar with as this method. And this method combines the facility location decisions with traffic equilibrium. And this method can be solved in a short time and can apply to a large-scale problem. However, since this is just an approximation method, so the accuracy is very low and the solution is not true optimal. Another approach is using the mixed integer program, which is a combination of this mixed integer program and this partial differential equations using the numerical method. So this model can provide a relatively higher accuracy, but it takes much more time to solve this problem. So it can only be applied to small or moderate sized problem. Also, due to the optimality gap and the discrete candidate locations, this method, the solution of this method is still not true optimal. So in our research, we want to find an algorithm that can provide both accurate and an efficient method to solve this location decision with traffic equilibrium. To achieve this goal, we need to dive into some kind of math. Now I will introduce some mathematical model. So first, let's introduce some mathematical definitions. First, suppose the entire service region is in a two-dimensional space, which is omega. This is the entire region. And all of the facilities are located at location xi. And each facility serves a sub-region ai. That means all of the customer in this sub-region will eventually choose this facility for service. And all of the other customers will choose other facilities. And also, the demand density at location x is a continuous function, qx. Also, there is a unit service price, which is a function of the total throughput, qi. Qi is the summation of the total demand in this subregion. So this is called the throughput. And also, we suppose that each facility occupies a small circular area. And this area is very small relative to the entire region, but it is a circular area. Also, we assume that the customer flux at location x is a vector field, which is called the F. And also, the travel cost per distance is a function of the flux intensity. So how to understand this? At some location, if the flux intensity is very high, that means the customer is congested here. So the travel cost is going to be a little bit higher. So that's why the travel cost is a function of the flux intensity. So we also assume that each customer chooses the best path that can minimize the travel cost as well as the service charge at the destination. So that as the user equilibrium, each customer is choosing the best path. So under the equilibrium, the total cost can be expressed by this formula, where this part is the travel cost along the best path, and this is the service charge for the facilities they choose. And also, we prove that all of the subregions disjointly forms the entire region, and they doesn't intersect with each other. Now, based on those definitions, we can prove that at the user equilibrium, the flux F and the cost U are described by these following partial differential equations. And this first one and the last one comes from the flow conservation law. And the second one is based on the fact that each customer is choosing the best path that minimizes the travel cost. And the third one is a boundary condition. This boundary condition means that no customer is entering the entire region or leaving the entire region. And the fourth one is also a boundary condition. This directly comes to the fact that if a customer is right located at the facility, the boundary of the facility, then the only cost is the service charge. So no travel cost is included.
So I think you have a typo there. The first line costs fine, right? Not you.
Oh,
First line.
first line.
Sentence, the words.
Oh, yeah.
It should be fine.
It should be fine.
We change the notation.
I'm sorry, though. So this one is not you, it's just this fine. Sorry about that. So due to the complexity and the nonlinearity of this PDE, it traditionally is always solved by numerical methods, such as the finite element method. But in our research, we are focusing on developing the analytical solution for this kind of PDE under some certain conditions to save the computation time. Now I'll introduce the method to solve this PDE. First, let's take a look at a simpler version of this problem where there is only one single facility. Without showing the tedious proof, I would directly put the conclusion here, where we state that if the following condition holds, the flux solution to the previous PDE with single facility asymptotically satisfies this PDE if the size of the facility tends to 0. Here, the flux field satisfies the curl-free condition, and the divergence of the flux equals to the demand density except for one point. Here, this is the delta function. And to solve this PDE, we introduce a new variable and a new equivalent formulation of this problem. Note that these two formulations are equivalent, so we want to solve this formulation instead of this. And in the literature, these equations are called the Norman problem because this boundary condition is of the Norman type. So to solve this Norman problem, I will introduce a new concept called the Norman function, which is the unique solution of the following equations. We can see that these two equations is pretty similar as these two equations. So, and also the asymptotic behavior of this Norman function near the facility is a log term plus a regular term. So this is an singularity terms. And with the help of Norman function, we can directly write the solution of the Norman problem using this formula. So this formula only involves the Norman function and the density function, and this is the constant. So the main task to solve this Norman problem, and it is also the main task to solve the user equilibrium problem, is to find the Norman function for the region omega. If we find the Norman function, we can directly put the Norman function into this formula and find the solution for the Norman problem. So now I will introduce how to find the Norman function for region omega. Fortunately, for some special shape of the region, we have explicit expression of the Norman function. For example, for unit disk, the Norman function is very simple, only involves two log terms and some other terms. Remember, this formula is very simple, and we will use it later. And for rectangle, the Norman function is a little bit complicated. It's a summation of a trigonometric series, but it is also in a closed form. And also for another shape is equilateral triangle. The Norman function is like this. It's a little bit complicated, but it is still in closed form. We can evaluate this normal function very fast. So to illustrate those normal functions, those are the shape of the normal functions and the corresponding flux pattern of these functions. This is for the unit disk, and this is for the unit square, and this is for the equilateral triangle. We can see that near the facility, there is a singularity point, which is caused by the log term. And this is the flux pattern, which shows the customer flux towards the facility. Here, the customer are not choosing a straight line to the facility. They choose a curved line instead. That is because they want to avoid the possible congestion near the facilities. So they choose a curved line to somehow avoid those congestion. So this is actually for some special region. We have a very easy approach to find the normal function. But how can we find the general region? So if the region is in an arbitrary shape, to analytically find the normal function, we should use some other methods. So first, we divide the normal function into two parts. One is called the S function, which can be expressed like this explicitly. And the other is called the U function. And the U function is a harmonic function satisfying a non-homogeneous Norman boundary condition. And the harmonic function means that the Laplacian is always 0 in this entire region. And so how to find the solution of this U? I will introduce another concept, which is called the conformal mapping. So conformal mapping means that it maps one region to another region without changing the angles. So how to understand this? Here is an example that maps the unit square to the unit disk. We can see that the grid lines are in the original region are orthogonal with each other, and the corresponding grid lines in the new region is also orthogonal with each other. So we are not changing the angles by the conformal mapping. So based on this property, we have a very nice property of this conformal mapping, which states that the harmonic functions in the original region are still harmonic in the new regions. So this is a very useful property. And based on this property, we have the following result. So first, if we can find a conformal mapping from our region omega to a new region D, and we can also, if we can also find a harmonic function in region D that satisfies this PDE, then we can directly write the solution U for omega using this relationship. And also, we notice that this kind of PDE is just the Norman problem, since this is the boundary condition is of the Norman type. And also, if for region D, if the D is the unit disk, since previously I introduced that the Norman function for unit disk is very simple. So this Norman problem can be easily solved and using analytical expression. So that means if we can find a conformal mapping from omega to the unit disk, we can analytically write the solution U. So this brings us the next result. If we can find a conformal mapping from omega to unit disk, we can directly write the solution U, because for unit disk, this Norman problem can be analytically solved. So this is the method that how we analytically find the Norman function for an arbitrary region. So for now, the user equilibrium problem for one single facility is completely solved. Now, I want to extend this method to multiple facilities. For multiple facilities, we also proved a decent property, which says that the flux solution for the PDE with multiple facilities can be expressed as a summation of multiple fluxes, and each flux is only related to one facility by this relationship. So this property actually provides us a decomposition scheme to solve this problem. So this scheme is like this. So in the first step, we solve the user equilibrium for each facility individually, but we don't know the scaling factor Qi, which is here. But it is just a scaling factor. The Qi is the throughput for each facility. And then we use a system of equations to solve for the demand partition Qi, and put the Qi back to this solution and find the fluxes for each facility. And finally, we add those fluxes for each facility up to get the complete solution for the original partial differential equations. To illustrate this whole procedure, I will show you an example. Here, we want to solve a two-facility problem. So first, we solve for only one facility, which is the upper one. And this is the user equilibrium solution for the upper facility. This is the contour plot of the potential, and this is the corresponding flux. And then we solve for another facility. So this is the corresponding flux and the potential. And then we use the charging function and the system of equations to solve for the demand partition. And one partition is the 0.69, and another is 0.31. And then based on this partition, we combine these two fluxes just by simply adding those fluxes and find the solution for two facilities. So this is how we solve for multiple facilities. And for more facilities, the method will be similar. So now we are able to solve the user equilibrium problem for multiple facilities and for arbitrary shaped region. So based on this framework, we also find some more properties for the solution of the user equilibrium. In fact, if the congestion function, which is the C function, is linear, the solution have many interesting properties. So first is when we solve the system of equations to find the partition Qi, we don't have to evaluate this path integral. Here, this is the path integral from location xi to location xi minus 1, which is two facility location. This path integral is not very easy to evaluate, but if the congestion is linear, we don't have to evaluate this. This can be replaced by this formula. Although this formula is a little bit longer, but this is very easy to evaluate since it only involves the Norman function, the density function. Those two are already known for the region omega. So we can calculate this in advance and solve these system equations very fast. And also based on these results, we have the following proposition, which states that if the charging function and the demand density function Q are bounded, then all of the Qis are equal if the size of the facility tends to 0. This means that the number of the customers patronizing each facility are equal. So how to understand this result? If the facility size is very small related to the entire region, then the congestion near the facility gonna be very extensive. That means the congestion cost is gonna be very high, and dominates all of the other costs, including the service fee and the travel cost. So every customer will choose facilities without considering the service fee and without considering the travel distance. So they only care about the congestion near the facility. So eventually, each facility will serve a same amount of the customer. So that's how to understand this result. Another interesting property is that if the Norman function is normalized and the congestion is linear, then the average cost per unit demand is the expression of this average cost is very simple, only involves the Norman function without any integration. So this simple expression will save a lot of computation time. Okay, with these properties, let's see some numerical examples for the whole procedure. So the first example is pretty similar to our previous paper, where we want to find the optimal location of multiple facilities in a unit square. Here, the entire region is the unit square, and we want to find the optimal location of the facilities in this square. And the demand density is non-homogeneous, which is higher at the left side and lower at the right side. And also the opening cost for each facility is non-homogeneous, and it is higher at the bottom side and is lower at the upper side. Also, the congestion is linear, and the service fee is also a linear function of the total throughput. So this optimization problem can be formulated like this, where we want to minimize the average cost per unit demand subject to a budget constraint for the building cost, and also subject to the user equilibrium equations. But fortunately, based on our previous framework, we find a closed form average cost based on these conditions. So this average cost is very simple expression with no integrations, and this average cost already satisfies the user equilibrium equations. So we only need to solve this equation subject to the budget constraint. So this is a very simple problem, and we can solve it using some standard nonlinear solver. So using the nonlinear solver, and based on the parameters given, and we find the optimal locations of the facilities in this unit square. And the minimum average cost is 4.87. And we can see that the facilities are more located at the left side and at the top side. That is because the customer demand is a little bit higher at the left side, and the building cost is lower at the upper side. So that's why more facilities is located at this part. As a comparison, in our previous paper, we use a Lagrangian relaxation algorithm with embedded finite element method. So this is sort of a numerical method. Using this method, we find the optimal locations like this, which is pretty similar like this, but the average cost is a little bit higher than our analytical result. Also, for the computation time, our analytical result only takes 4 minutes to find these optimal locations. But for the numerical methods, it takes more than 10 hours to find the optimal locations. So which is much slower than our analytical result, and also provides a worse result than our optimal value. So as another example, I will solve for the user equilibrium for an irregular region and even a non-convex region. The boundary of this region is given by this parametric function. And the normal vector along the boundary is given by this parametric function, which is a very complicated expression. And also, we find a conformal map between this irregular region and the unit disk. Here we can see the grid lines. For the irregular region, those grid lines are orthogonal with each other. And for the corresponding grid line in the unit disk are also orthogonal with each other. So this is a conformal map. The expression is like this, which is also a little bit complicated. So based on this conformal map and our previous framework, we can use a nonlinear solver to solve for the optimal location given this function and parameters. Here, this is the optimal locations, and this is the optimal value. Here we can see the facilities are more located near the boundary of this region. That is because based on this definition, the building cost is a little bit higher at the center part of the region, and it's a little bit lower at the near the boundary. So that's why the facilities are located near the boundary. And as a comparison, the previous numerical method gives this result, which is a little bit worse than our analytical result. And also for the computation time, our method takes about an hour, and the numerical method takes more than 11 hours. Here, I should say that this computation time is longer than the previous unit square case. That is because the Norman function provided by the conformal mapping is not normalized. So we need to use a numerical integration to normalize this Norman function, which takes some extra time. That's why this is a little bit longer than the previous one, but the time is still much shorter than the traditional numerical methods. Okay, now to summarize, let's quick look at the main points of our research. First, we develop a decomposition method for solving a class of continuous user equilibrium traffic behavior for multiple facilities and for arbitrary region. And next, for some specific cases, we have a closed-form user equilibrium solution. And also, for an arbitrary shaped regions, we develop a conformal mapping scheme to find the analytical solution. Also, for some specific cases, we have a closed-form optimization formula to find the true optimal solution. This saves us a lot of computation time and it gives us a more accurate result. Okay, that's all. Thank you.
Questions? I have one. So this problem that you mentioned at the beginning happened in Hajj. Just the background on that problem, I was reading something about that, is there was an original route that normally people would go to that stoning facility. They closed that route for no explained or disclosed reasons until now. So they don't say right now why they closed that normal route. So they diverted people to a different route, which that incident actually triggered that incident. So that's just the background on that story. That's just because normally they were always going from that route, which is much wider, I think, a trail where they had no incidents before. There were other incidents in the Hajj, but at least for the stoning facility, they didn't have anything before. That's one background. And question is, what is the significance of working with irregular boundaries?
Irregular boundary, if we can solve for irregular boundary, we can solve for any real cases, because for any real cases, the boundary are mostly irregular. For example, a city or a random city or a random park, which is of an irregular boundary. So if we can solve for arbitrary region, we can solve for any application.
More questions? Nothing? Nobody's moving? Nothing, your head and something.
What is the unit of the cost?
I'm sorry.
What is the unit of cost? Is it money or is it dollars or, you want to minimize that cost, right? What's the
The cost always related to the travel time or the travel delay or something like that. Yeah, for the facility,
Actually, you have multiple solutions, right? You have like I saw the figures like many dots, right? So it doesn't matter which one you're gonna choose, right? They're the same, right? In terms of travel time. Do you have any application of your theory, like methods? Every case that to design for the facility.
we're going to use this method maybe to solve some real cases. But for now, we only solve for some hypothetical cases.
You have some backup slides maybe to show some of the train station. The question is about the potential application to the real world.
Actually,
About the next steps.
yeah.
Or some, maybe.
For some real cases, for example, this is in a some kind of fire accidents where people are trying to escape through a door. But if we add some barriers here, that will improve the efficiency and release the congestion. This could be a possible application of our method. And another is in a,
Robert, are you, does this include the human psychology? Because what happened in high distance, they panic.
yeah.
When they panic, they started to move faster, and that's what they couldn't, they know not squeezed, and then some of them were just pushed against the fences, and the other were just couldn't really couldn't breathe. That's why they died. And does this include, like in this kind of a blockage, for example, there will be also panicking.
Oh, yeah. You mean they will destroy those blocks?
I think in this case is actually what you said is right, but this is really trying to show when people over congest, the system breaks down. So even when you give artificial blockage to the people, we actually could make people better off. So it's a little bit counterintuitive. We artificially block people, they can actually go through faster. So this is actually something that one thing that we are going to try to see how we can design those blockage. You can imagine, right, adding boundary condition to the partial differential equation to try to see where do we actually block people would be the best. That's actually something that you have been working with the visiting student. Right?
Okay.
So that's one thing.
Channelization, guidance for, yeah.
That's one of the things we're going to next. Right now we're not there yet. We're not be able to solve this problem particularly, but we are working on it as we speak.
Another application is in a metro station where people want to evacuate through the metro station. If we add some guidance or if we add some walls here, that will improve the efficiency of the exiting.
The bottom is the train, right?
Yeah.
The metro station. People try to get out. You have animation, I think. Why don't you show the animation? You can just show the animation, but on the bottom. There's animation. I recall. Yeah, go. This is hiding a blockage. This is actually some people in Chile. There was a lot of congestion on the platform. People travel around to try to cross each other on the platform, which is very congested after the train arrives. You can see the bottom is the train. It's the best drawing we could have. But then they are trying to get to the different stairs to get out of the station. And then, so the people in Chile, right, they put this barrier to block one-way traffic. Then it turned out that actually, just by adding blockage, again, they are able to observe 5% improvement on the reduction in travel time, 15% of capacity increase. That means the number of people that can get out per unit time. So it's quite amazing. It was also something that they just did it without any theoretical basis. They just did it. They're smart, of course, but but we thought that our model could be used to try to tell them what to do better.
So that's the right side is the actual case. They have the
Yes,
the
we have
barricades?
implemented in 2013. The left-hand side is before. They have video even to show people just shout water. You know, they're not very nice to each other. They just do this, shoulder each other. But then after the blockage, actually, some people gets blocked without movement. So they streamline the traffic a little better, and then we were able to get through. So this is another thing that sort of motivated us to start looking into this. We want to build a model to help them even better design where we should add blockage. Whether it's better to add blockage, we have a theoretical model to show that, to predict before they actually go do it. Right?
What are the best application of those barriers?
And even for the previous one, previous one, please. An interesting one. Oh, you have yeah, this one. Even for this one, we were trying to see what is the optimal blockage. Even think about the channel should narrow down gradually. We're thinking about what is you were doing experiments on trying to see what is the best way to narrow down maybe it's not best that you just have a sudden narrow down of the gate, right at the gate. Whether you should have a gradual reduction of the width of the channel such that people get adjusted along the way, and then the throughput may be better. That's something that maybe we should divert people away from give them some fake doors.
That's the dead end, right? That you designed there. There's a dead end.
Right. That's actually this is actually
That's if you go there, you'll be killed.
That's actually motivated us to try. This is actually not our work. This is some European physicists.
Okay.
They published they published papers in Nature Science. They were trying to say that people are complicated. They were trying to say, oh, people are complicated. We block them, we divert them, we give them fake doors. They do better. So we were trying to build a model to try to so they did simulation, they did experiments to show that's happening in the real world. We are trying to build a model to explain it and then try to do better with a mathematical basis. So that's sort of another motivation we were doing that. And he has been, I think, Dodong, you can speak more, right? You are working with a student to do experiments on this type of things.
Another model, which is the current model, but solution methods.
Yeah.
Just don't try on us. If you are conducting an experiment.
I was thinking about HR. Fake doors.
It would be fun though. Could be like an HR bonding.
So don't be surprised. Don't blame me. Fake door somewhere.
Now, when I see a weird design, that will always remember when we evacuate the building. All right, nice discussion, I think, right? Any other questions, comments? In that case, I want to thank really Zoltan for this great presentation and the nice discussion after math. So I'll just give him an applause.